Welcome to the course of Database Management Systems. I am Chenhui Zhang, known as Tracy in my department, from the University of Alabama at Birmingham. In this course, we'll be learning about databases and the use of database management systems, primarily from the viewpoint of the designer, user, and developer of database applications. I'm going to start by answering two basic questions. Why study databases and what is a database? Database systems are almost everywhere in the world today. They sit behind many applications and websites that will run your web search engines, online shopping systems, banking systems, your telecommunications, sensor network, scientific data, and much more. Database development and research also offer many exciting job opportunities, such as database application developers, database designers, database administrators, and database engine implementers. Those jobs are highly paid and play very important roles in the entire process of database products and development and deployment. Database systems are almost everywhere in the world today. They sit behind many applications and websites that will run your web search engines, online shopping systems, banking systems, your telecommunications, sensor network, scientific data, and much more. Database development and research also offer many exciting job opportunities, such as database application developers, database designers, database administrators, and database engine implementers. Those jobs are highly paid and play very important roles in the entire process of database products development and deployment. This course covers some of the most important tasks carried out by database designers and database application developers. So, what is a database? What does the database management system provide for applications? A database provides a means of handling large amounts of data efficiently, reliably, conveniently, and safely, allowing storage of and multi-user access to massive amounts of persistent data. I know this is a long sentence. More details will follow when we talk about the common characteristics of a database management system. So, put it simply, a database stores a large collection of related data. That's where the name of relational database comes from. If there's no relationship between data, it's probably not worth using a relational database. And the data stored in database are known facts that can be recorded and have an implicit meaning, such as student grades and transcripts, and the courses students take. Database Management System, abbreviated as DBMS, is a software package or system to facilitate the creation and maintenance of a computerized database. And the database system, or a DS, includes the DBMS software together with the data itself. And sometimes the database applications are also included in the database system. Here's a concrete example of a database system. Okay. Here's a concrete example of a database system. Let's take a university student information management system as an example. The data objects stored in this database may include students, courses, sections of courses, academic departments, and instructors. However, it's not sufficient to store just the objects or entities in our database. We also need to store their relationships in our database. There's some relationships between and among those real-world objects in this database. For example, the sections of courses, and students can take sections of courses, and courses have prerequisite courses, and instructors teach sections of courses, and courses are offered by departments. Students major in certain departments. Okay, and there are many more relationships in this database. One other example could be some students can serve as the TAs for certain sections of certain courses. Okay, and I'm going to redo this. So here's a typical example of databases: a university student information management system. The data objects stored in this database may include students, courses, sections of courses, academic departments, and instructors. However, it's not sufficient to store only data objects or entities without storing the relationships between and among them. For example, what if we want to know which courses a student is taking? Or what is the average GPA of all the students in computer science major? In order to answer the first query, we need to store in the database the relationship, say, course taking, that connects students to courses. To answer the second query, we need to store the relationship between students and department they major in. Examples of other relationships include sections are of specific courses. Students take sections of courses. Courses have prerequisite courses. Instructors teach course sections, and courses are offered by certain departments. Students major in departments. There are many more relationships between and among those objects. One other example could be certain students serve as TAs for certain sections of certain courses. So the next natural question is, why do we need database to store this data? Why not use a traditional file system? So here's file system versus DBMS. In a conventional file system, such as the Windows file system, or a Mac file system, or even a Unix file system, they fail to support efficient search and use linear exhaustive search for queries that involve non-indexed content. For example, if you want to search if a file contains a particular string, a linear string matching will be performed for each file stored on your computer, character by character, file by file. Another example is search by a particular date. There are so many different data formats for the date, and to retrieve all the files that include a particular date, you will have to perform as many exhaustive searches as there are different date formats. Okay? For example, you will have to consider date formats such as June. I'll redo this slide. Here's a side-to-side comparison between traditional file systems and database management systems. Traditional file systems fail to support efficient search and use linear exhaustive search for queries that involve non-indexed content. For example, if you want to search if a file contains a particular string, a linear string matching will be performed for each file stored on your computer, character by character, which is not very efficient, obviously. Another example is search by dates. There are so many different date formats. For example, today is June the 11th. Okay, And you can represent the state as 06. Okay. Here's the side-to-side comparison between file systems and database management systems. Traditional file systems fail to support efficient search and use linear exhaustive search for queries that involve non-indexed content. For example, if you want to search if a file contains a particular string, a linear string matching will be performed for each file stored on your computer, character by character. Another example is search by dates. There are so many different date formats. For example, to represent today's date, which is June the 16th, 2016, there are different formats you can choose from. For example, you can represent the date as 06/16/2016, okay, separated by a forward slash. Or you can represent the same date by saying June 16, 2016. Okay. So if you want to retrieve this particular date from all the files stored on your computer, you will have to perform as many exhaustive searches as there are different date formats. This is an example that shows the traditional file systems lacks the capability of performing typed structured queries because the data stored in the file system is largely unstructured other than characters, bits, or bytes. Conventional file systems also fail to support complex queries. For example, try to find all the files that include a number less than 5 and greater than 0. There is literally no way, or at least no efficient way of answering such a query in a traditional file system. Again, this is due to the fact that data is stored in an unstructured way in a file system. Traditional file systems also fail to support sufficient modifications to small pieces of data due to the use of exhaustive search in most cases. Therefore, locating small pieces of data is time-consuming. Update is often error-prone. No constraints can be enforced. Updating a small piece often causes the entire file to be rewritten. For example, if we say that an employee cannot be younger than 18, there is no way to prevent the insertion of an employee younger than 18 into a file that contains all the employee information. In another example, if we try to modify the name of an employee from John to Jones, all we need to do is to open the file of the employee and insert an additional character S after John. It sounds easy. However, after the update, every subsequent character following John will be updated and pushed one position down in the file, resulting the entire file to be updated, although we change only the name of one employee by one character. This is because the minimum unit managed by a traditional file system is a file, not a field or attribute, such as an employee name. Traditional file systems also fail to support controlled buffering of useful data in main memory because the file system has no idea at all about what is useful or not in terms of the usage of that data by a database user. Why? Because there's neither implicit modeling of connections between and among files in a typical file system, nor is the data structured. For example, in a typical banking system, the user table is closely related to the account table. Whenever the user is queried, the account or accounts associated with that user is often queried as well. So it is desirable to buffer the account together with the user. However, such connection or relationship is unmanageable and thus invisible to the file system. Traditional file systems also fail to support independent execution of transactions, especially when there are multiple database users who are accessing and updating the database at about the same time. We will get into more details later on this issue. So, in short, a file system at most provides support for file object management, just like the concurrent control and version control are done all at the file level, but no support at all for managing relationship between or among data objects. There are other issues like data integrity, consistency that the file system is not able to address. In contrast, database management systems, or DBMS, supports users to create databases and specify their own database schema, and also supports users to query and modify the data at a very fine granularity. For example, you can just modify the employee name of one single employee without updating the others. And it supports efficient storage of very large amount of data, secure the data from accidental or unauthorized use, and allow efficient access and complex queries. It supports control concurrent access from multiple users, presenting correct, consistent data to each user, and prevent accidental corruption of the data from simultaneous accesses. And this is called the atomic and independent execution of transactions.